All right. My name is Mike DeLaCluse, President of Lesman Instrument Company. I'd like to thank all the attendees for taking time out of your busy schedules and to join us for today's webinar. After today's webinar, you'll understand the difference between concentration measurement and density and have some insight into which is best for your application. Many of our customers ask for a density measurement when what they're really doing is using it to calculate concentration. When you infer concentration, there are errors that can be introduced into the process. And we hope after today you'll be enlightened as to when using a refractometer may be a better method. We're honored today to have Eric Gronowski from K-Patents as our presenter. Eric is the U.S. National Sales Manager for K-Patents, and for the last 8 years has been helping customers optimize their process by implementing refractive index measurements. The phone lines are muted. If you have a question, there's a question tool in the GoToMeeting interface. Please type in your question and I'll make sure it gets answered. With that introduction, I'm going to turn it over to Eric.
Thanks, Mike. Again, as Mike had mentioned, I'm Eric Gronowski, and we'll be talking a little bit about examining density and refractive index technologies for making inline concentration measurements. Now, Lesman has a number of, and you as well as a customer, have various measurement technologies in your toolbox. It's very similar to the tools in your toolbox. Screwdrivers and hammers, and what you'll do is that at any given project that you have or task that you're going to undertake, you need a specific tool. And the world of process instrumentation is very similar to that. So you have to choose the right tool for the job. In instrumentation, the primary function is to provide accurate and real-time information of the process. And if you have that information, you can do specific tasks like improving your product quality or improving your financial performance by optimizing such as like a raw material savings. You can also improve ecological and environmental performance of the process and eliminate the need for any kind of process interruptions. This also could be a safety tool if you have correct information real time, as you can prevent accidents and any kind of injuries from happening. But which instrument is the right tool for the job? Well, you have to compare your advantages and limitations for each task at hand. Now, specifically, this presentation's focus is going to be in the measurement of concentration. Of course, before we talk about that, I wanted to define concentration and to explain what that is. Well, concentration is a relative amount of a given substance contained within a solution of a particular volume and space. Usually that's percent by weight. So, for example, if I have this 25 pounds of a caustic or a sodium hydroxide flake, and I mix that into 75 pounds of water, that resulting mixture equals 25% by weight in 100 pounds of solution. Now, in order to measure concentrations, and as far as you can measure a density at measuring a concentration, and probably one of the most simple ways of doing that is using a hydrometer. And the principle of a hydrometer works that a floating body displaces its own weight in a fluid. So if you float that hydrometer in that picture with the green background, you float that hydrometer into the liquid, that specific gravity or density is determined by the scale on the stem of that hydrometer. On the right-hand side, I picture something. It's a little more historical. As a child, I remember a grandfather having one of these for his car. He would be able to either pull up a acid from his battery or even glycol concentration by siphoning off some of the material into this hydrometer. And based on the calibration onto that stem, can determine if that concentration was optimum for the particular material that he's bringing up through this hydrometer, portable hydrometer. Well, density instrumentation is very similar. You know, the hydrometer idea translates into these instruments, and so if you have a density of a material, you can arrive, much like when you have this hydrometer, is the concentration of that liquid by taking the specific gravity or density of that known material. Now specifically, I'm going to focus on Coriolis density measurements. I find these to be the most common way in industry to be calculating at a concentration. And we'll talk a little bit about why I think that is, but the density measurement for Coriolis is a direct measurement. It works on a principle that the period of oscillation of the flow tubes is related to the density of the liquid in the flow tubes. So if you see on the top right side, when there's no liquid moving through the Coriolis tubes, the tubes vibrate in phase. But then when you put a liquid flow through the tubes on the bottom right side, you'll see this phase shift, and the monitoring devices on these tubes will give you a measurement of that phase shift, which is actually a density of the material flowing through those tubes. But calculating concentration as a function of the specific gravity is really an indirect method, which actually can come some issues that we'll further discuss in a few more slides. But these density measurements of Coriolis can be various different tube shapes and arrangements. Some of these give you improved performance, sensitivity, or signal-to-noise ratio. Some of these have a special purpose. Some are sanitary or single or double tube. Some are polymer lined for aggressive acids. Sometimes these differences are very much perceived from manufacturer to manufacturer, or also in avoidance of any kind of patent infringement. So, but all of these Coriolis designs are doing the same thing, and that's measuring that phase shift of the tubes based on the density of the material. Now, manufacturers commonly use Coriolis mass flow, and why is that? And that's because multiple measurements can be made. It's almost like a Swiss Army knife in the instrumentation world, is that the primary measured variables, mass flow, density, and temperature, can be used to derive any other variables such as volume flow or total solids or concentration. So like a Swiss Army knife, there's many things that can be can be arrived at from the same device. However, when in instrumentation are concerned, there's comfort in the familiar, but also there's a problem. And when you have a comfort, you know what to expect from that measurement, and the maintenance personnel knows how to troubleshoot and recalibrate and maintain that specific instrumentation, because there's a lot of them in the field, and that's good. However, the downfall of doing that is that you might miss out on something better for the task at hand, and that is specifically a tool made for the task of measuring concentrations. So in theory, using density for concentration percentage, this is a graph of a concentration of a sucrose curve, and that would match a standard chemical table. So as the concentration goes up, the density goes up specifically. And when it's calibrated perfectly, the accuracy using density measurements or mass flow can reach a plus or minus 0.1% by weight. However, in practical and the real world applications and process conditions, there's always something. And so sometimes the Swiss Army knife, when you have multiple measurements being made, maybe you need something specific, more like a hunting knife for that task. So is it accurate enough specifically for concentration measurement? So let's illustrate a couple of situations that may happen in process conditions that will affect real-time density technologies. So in a density measurement is amount of mass per unit of volume. But what happens if the blue balls in this box are represented by entrained air or a gas? In a case of very small, homogeneously dispersed small bubbles, more power is required to vibrate those tubes. And any kind of separation of a gas phase from a liquid phase creates a damping effect on that vibration, leading to a measurement error. So error is a real problem when you're using density measurements, because it changes the density and creates a completely different concentration based on that calibration and calculation. Well, sometimes that accidental error or gas entrainment for online applications is completely unavoidable, such as a case where you have a free-falling fluid discharge. So the pipe flows into this vessel, and the pump inlet is pulling those bubbles into your process. Or any kind of agitators being used will suck that air in, creating bubbles. And very common, these cavitations, any kind of bubbles are created also in more common things like pump and valve seals, leaks in the piping create these bubbles. So they're just unavoidable, and it happens. And that is going to throw off that calculation to concentration. Let's look at another case. In the same density, in the same box of materials, what happens if those orange balls that are in this material represent a suspended solid, such as a pulp in a juice, or crystallized sugar, or corn or wood fibers, such as a brown stock washing application? Anything that's undissolved within this is also going to change that concentration reading when we're talking about density, because of course that material is going to be more dense because of the solids within that stream. So that becomes an issue. Furthermore, what happens if the yellow balls in this box are represented by various hydrocarbon liquids undissolved in a sulfuric acid? That's something that's common in an alkylate for the oil and gas industry, or even drops of oil in a hexane. So that measurement is going to be a total solids measurement, which is going to give you a total density mixture of the oil in a hexane or the hydrocarbon liquid that's undissolved within that sulfuric acid. So these are real issues for or problems by using Coriolis mass flow versus the direct measurement of concentration. So there is something specific out there that can eliminate all those three issues I just mentioned, and that is refractive index. And to go over the technology of refractive index, it's the difference of the speed of light in different process mediums. So N is its refractive index, and that is basically the speed of light in a vacuum divided by the speed of light in a particular medium. So let me give you a little bit of a picture here. So when the ray of light passes from one medium to another, it's bent at an angle because the change of the speed from the air changes with the speed of light in that liquid, whatever that liquid may be, whether that's a sugar solution or an acid solution or a caustic. The specific bending or angle of incidence is very different for each individual material. So determining that solution's refractive index is a direct method of its concentration. And the takeaway of this presentation, and a very important note, is that refractive index, or N sub D, by the way, N is refractive index, and the D represents the sodium D yellow light. That's the wavelengths of light specified in the chemical tables. But that is not influenced by bubbles or particles. So that light speed is going to remain the same, even if there's quite a bit of bubbles or particles. So we'll talk about the laboratory technology, both a lab and inline. This on the upper right-hand corner is an example of a laboratory refractometer, and this lower left-hand corner is the laboratory refractometer. And it's the same as a K-Patents online refractometer, is that when this light shines through a prism, some of that light is absorbed into this liquid material, but at the first point of a reflection causes this critical angle. And this critical angle creates an optical image, an oval, and the line changes between light and dark based on the concentration of that liquid material. So if you look into a handheld meter, this is what you see. you, as an operator, need to look through this eyepiece and put a couple of drops of sample onto this window. You will see this line, this blue line between light and dark, and then try to determine where that line falls on a scale. So in this particular case, I have a scale of a battery fluid, or even an ethylene or a propylene glycol. So it'll give you a concentration measurement as you look through this the viewfinder. And as the less light is a higher concentration, but that calibration scale can be also other things such as bricks, which is very common when you're buying them from any kind of a catalog house, online refractometers. Well, that principle is the same thing in online process refractometers. That optical image is created by the phenomena of refractive index and projected onto a CCD camera. That's a digital camera. The digital image is shown on the refractometer. It gives us high pulses for the light and low pulses for the dark. Well, the interest is much like a human eye deciphering that optical image. Where does that line fall between light and dark? And when we find that line between light and dark, we know it's refractive index. If we know it's refractive index and temperature with the material, then we can know its concentration percent by weight. So as I mentioned, probably one of the most key points to this presentation is that there's no measurement errors created by particles or crystals. Also, bubbles and colors don't affect this measurement. If the light reflects off a bubble and ends up into the darkened area, 30 years ago, that was an issue because you were counting how much light is reflected back. But the advancements of digital camera technology gives you a measurement of the line between light and dark, much like the human eye would decipher, and ignoring any dark pixels on the camera that are error and ignore as part of noise. So that's an exclusive advantage of K-Patent's digital and direct measurement technology. So bubbles, suspended solids, any kind of vibrations, flow changes, pressure, temperature don't affect or otherwise interfere with K-Patent's concentration measurements. All those issues are real issues when you're using density measurements, because all those issues are going to give you a problem. So in the same regards, refractive index also has an exact calibration as that matches that standard chemical table. So as the concentration goes up, you'll see that refractive index, or N sub D, also rise. But in practical issues, the accuracy is plus or minus 0.1%, even in less than perfect conditions. So you're still getting those accuracies when there's more or less bubbles, when there's more or less crystallized or undissolved particles within that liquid material. If there's vibrations and temperature shocks, you'll still get those accuracies. And the reason is because it is the direct physical property of that liquid material. How do we know? These instruments can be individually verified and traceable to international standards. So you'd have bottles of refractive index liquids, and you'd pull a unit off the process and put it on the tabletop. And as you drop the certified refractive index liquids, you could print yourself out a verification document proving that this unit is still calibrated. Now, generally this is done because this is a digital device. Refractive index or K-Patent's refractometer will not drift over time, but you can verify that based on your own documentation and on the process that you're making the measurement on. That's important because that's something that to do a full verification of a density technology or tool, specifically a mass flow, you would have to put that onto a skid, and you can always measure a zero by putting water through it, but you can never do a full 0 to 100% calibration unless you put onto, take it out and put it on some kind of test stand. So how do you determine this suitable technology? First of all, you have to ask yourself, well, what is the process, and what are the process medium that you're measuring? And also, what is the desired measurement? So in short, we're going to call it the P, the PM, and the PM squared. Process medium, and then the process medium measurement. So we'll go over a couple kind of specific applications that to illustrate kind of my point between density and refractive index. So you have to understand the reason behind that concentration measurement. How is that measurement being used? And there's 2 points in this starch sweetener process that I'd like to illustrate. One being this evaporator process. This is probably one of our most common applications. Anytime you're putting water in or taking water out of a solution is a perfect example or application for a refractometer. In this particular case, you have inlet of the evaporation process is very good to know, because now you know the concentration of the liquid material coming into the evaporator. So for instance, what you can do is then monitor that feed forward and control the amount of steam that's needed to boil off the liquid. So what you can do is, if you know what's coming into the process, then you can control your steam and save on energy costs. And then also, of course, what makes even more common is that the outlet of the evaporator. What's coming out of the evaporator is that finished product. Now you know, has that worked correctly, and do you have that liquid concentration in that targeted range? So if you're looking for okay accuracies, that mass flow is okay for that particular application. But if you're really looking for fine-tuning that information coming from that evaporator or going into the evaporator or coming out, you can use a refractometer. I'll also talk a little bit about this dextrose application and this crystallizer. This is something very unique to the industry, because there's quite possible situations where you can use multiple technologies to provide more process information. So let's go a little further into that particular application, and this is a real-life application example where both a density and a refractometer, refractive index technologies are needed at the same time. If you're not familiar with a crystallization application, I'll review that here. So what we have is a thick juice going into these sugar pans or vacuum pans, 1 through 4. And the crystallization is initiated by seeding that concentration liquid, that liquid, by using a starter crystal, or which is a solid. So as you reach a concentration level that's optimum, you seed the liquid material, and the crystals start to form. As that process continues, that liquid concentration percentage starts to drop as more of the liquid sugar starts to become a solid crystal sugar. So what we say, and what the industry says, is to optimize this process. Obviously, you want to keep that liquid in a steady, supersaturated state. That's a key. So basically, if you don't have that, what you're going to have is, as that liquid falls out of the supersaturation state, your crystals are going to start to form slowly, and you're going to have a lot of starts and stops in your crystallization process based on that liquid concentration only. It's very difficult to look at that liquid concentration by using a total density, because you're getting a total solids. So let me show you this graph here, and it kind of illustrates what I'm saying. Is that the blue line represents total solids coming from a Coriolis, or even any kind of density measurements like a microwave technology. And also, green line is the level within that vessel itself. So what happens at this vertical line here is the point of your crystal seeding. So as this total solids, or a concentration of your liquid material, only goes up and the seeding process begins, what you'll see is just a rise of the density of this liquid material. However, this red line here can specifically show you that liquid concentration only. And as the seeding process begins, you can look at the supersaturation, which is shown on this right-hand side, and the optimum level is between this 1.1 and 1.2 ratio for supersaturation. So you can see what's happening in the liquid stages, so you continue to feed that concentration liquor to the same supersaturation state, and then you'll get fine crystals and conglomerates. It's a very good application for crystallization applications, and it's very necessary to have both your density as well as refractive index. So continuing on the PM, knowing the process medium. Well, is that liquid material liquid or gas? And a refractometer only measures liquids, where Coriolis can be both liquid and gases. Are there any suspended solids like that crystallization application? And is it desirable or undesirable to factor in those suspended solids into your measurement? Do you want to know liquid portion only or total solids, liquid and the suspended solids? Is the material itself a harsh or a chemical or an acid material? So what you need is specific materials needed for that corrosive process environment. But also, you want to look up the physical properties of those process mediums. So it's very useful to look up the RI and density values of a process medium. Now I have a case specific to that. And that is when looking at physical properties, there's a liquid hydrocarbon identification application. So in chemical plants and refineries, they receive and deliver all kind of different liquid hydrocarbons. Including natural gas liquids, which transported by pipeline, rail car, tanker trucks. Some of those products are very similar in properties and appearance. So therefore, proper identification or interface detection between these hydrocarbons are very important to ensure quality assurance from the supplier, but also making sure that the correct material is connected to the correct storage vessel. And in this particular case, I took a real-life situation where two typical products that require that process interface detection are N-butane and isobutane. So these are two structural isomers of butane, meaning the same molecular formula, but a different arrangement for the chemical structure. So ultimately, because they're isomers, the chemical properties are in particular the density, are very similar and too similar to use a mass flow Coriolis. However, the difference in refractive index, which is repeatable to a plus or minus 0.0001 RI, is wide enough to accurately and reliably distinguish between these two particular materials. So as you see, the butane has the same formula as a normal butane. It's the same molecular weight, and the density is the same. However, those refractive index are very different because we're measuring refractive index into that fourth decimal point, where the changes are beginning into the second decimal point. Very, very easy to determine between. So that's a good example of using the physical properties and the correct tool for the job to give you an idea of which one is N-butane versus isobutane. We also have the PM squared, the process medium measurement. What's the goal of that measurement? Are you looking for flow only? Perhaps you're looking for a density measurement, but are we looking for a true density measurement or total solids, including the suspended solids, or only a liquid density, where the suspended solids or air are not desired into that particular measurement? That would be a truly concentration measurement. One of the examples of the measurement is how are these measurement techniques being used not only in the process currently, but also in the laboratory. And what is the acceptable accuracy range? Is good enough, or is the goal in your particular case for concentration measurements great? Here's a real-life application note specific to the process medium measurement. And it's in, this is coming from corn.org. There's all types of different recipes of corn syrups and dextrose equivalents. And each one of these dextrose equivalent recipes has very specific makeup of the different sugar chains. And what happens is in the laboratory technology, they often use the N sub D or refractive index. And the reason is because that refractive index concentration curve is going to be the same. It's going to be refractive index no matter which one of the recipes is selected. However, by using density to arrive at your concentration, you would need a density calibration for each individual material. So if you're switching between a 53 dextrose equivalent corn syrup and a 63, or into a high fructose corn syrup, the density is going to be very specific and very different for each one of these materials. So your calibration to a concentration also has to follow. You'll have to have a concentration specific to those materials, where refractive index is the same technology as the lab, so no changes in that measurement calibration is going to be necessary. So let's review differences between the refractometer and that Coriolis mass flow. The refractometer is going to give you two measurement readings, your refractive index and your temperature. And Coriolis mass flow is going to give you up to 4 measurement readings: your mass flow, volumetric flow, temperature, and density. The refractometer is going to measure true dissolved solids measurement, liquid components, or the Coriolis is going to give you a true density measurement or direct mass flow rate measurement. Refractometer pipe size does not affect the cost. We're going to have the same unit for a 1/2-inch line as we are going to have for a 36-inch line. A Coriolis mass flow has a very low cost for smaller pipes, but as the pipes start to increase, the costs for that start to increase as well. So, just to answer one question that comes up, where is the crossover between that? And I'd say that about in that 3-inch size, that's where the Coriolis starts to become more expensive than using refractive index. There's no moving parts to a refractometer. There's basically a light source, that LED that shines through that prism and into that camera. Coriolis mass flow is a little bit more maintenance because there are moving parts. There's flow tube forces at play onto those tubes. In addition, we talked about the easy calibration or on-site verification of calibration, where mass flow you would also need to perform that verification onto a test stand if you're doing something other than just a zero check or pumping water through there. So in essence, the refractometer gives you a high measurement accuracy of concentration, where the Coriolis gives you a good measurement accuracy. So we talked about the refractometers being liquid only, and the Coriolis can do liquids and gases. Bubbles and trained air vibrations do not alter the measurements, where those measurements for the Coriolis are affected by entrained air, external vibrations, and stress on the piping. Refractometers can be installed in various pipe sizes, where Coriolis mass flow is unique to the actual pipe size of your application. So you have to order that specifically for a 3-inch or a 4-inch line. Now there's a coating is a possible. Being an optical device, there's a potential for a coating, and what we have is an in-situ flush that is able to blast a steam or high pressure water or water across the prism surface face, integral to the probe right at the prism surface. So you just not have to flush the whole line to keep this measurement going, but only a 1/4-inch diameter prism surface on the tip of the probe. Where in Coriolis, if there's any kind of coating or buildup within these tubes itself, you'd have to flush out the whole entire line. So there's a lot of waste involved, where something of this coating or buildup in situ prism flush, you can do that in the process as long as that 3 to 4 second blast of steam is okay to integrate into that process. So our unit is a digital device. It won't lose calibration over time, where the Coriolis mass flow is a mechanical device. And we also do have probe types that can be used directly into a tank or a vessel, where you would need to flow through a tube for the Coriolis mass flow. So I think at this point, I wanted to thank you for attending this webinar. And also my contact information is at the lower right-hand corner. If you'd like to have any specific questions, certainly please contact me, and we're going to open up the floor if there's any type of questions.
Eric, I've got the question tool open, and so far we don't have any questions. So we'll start to wrap it up, and as I'm doing that, if anybody has any questions, please send them over and we'll make sure we get them answered. Eric, thank you very much for your presentation. Again, if any of the audience has any specific questions, feel free to give us a call. You can reach me at 800-9-LESMAN or 800-953-7626. If you don't know your account manager, again, feel free to ask for me and I'll make sure that you get taken care of. All the products discussed today can be found on our website at lesman.com. If there are some future webinar topics that you'd like us to cover, please send me an email with the subject. We have access to a lot of product specialists, a lot of different products. So if you let me know, we'll see if we can get them covered. You can just email that to me at miked@lesman.com. Next month, our webinar topic is going to be accurate flow measurement in changing process conditions. Specifically, we're going to go over multivariable transmitters and the different ways that you can use them to gain accuracy in your process. That's going to be on Tuesday, March 28th, again at 9 a.m., and it's going to be presented by Lesman's own Dan Wisey. For more information, you can go to our website and sign up at the Lesman Training Center. Eric, I still don't have any questions, so you did an absolutely wonderful job.
Well, that's okay. If anyone's too worried to speak up, they can contact me, but that must mean it was a great presentation.
That's for sure.
Thank you very much, everyone.
All right. Thank you, Eric.